in this video, we are going to discuss about practical operational amplifier. So, which is non-ideal. Okay. So, what does non-ideal means? For ideal, the RI value is infinity, right? So here it is not infinity. Whereas R naught value is 0. So here it is not 0. Gain value is infinity. So here it is not infinity. Okay, this is for open loop gain. So what is open loop gain? Open loop gain means there is no feedback. So here you can see this is equivalent circuit of practical op-amps. Okay, so it consists of V2. V2 is nothing but an inverting terminal, and this one is non-inverting terminal. Okay, and this is my RI. Okay, so the difference, so this is called as a voltage controlled voltage source. And R naught is your output resistance. Okay, so if I from this I can calculate the value of V naught. V naught is nothing but A VID. So where I can write this VID is equal to V1 minus V2. Okay, because V1 is nothing but a non-inverting terminal and V2 is a inverting terminal. So let us discuss about the LM741 operational amplifier. So it is a general purpose operation amplifier with which features improved performance over the industrial standards like LM7409. Okay, so this LM74 is identical to that of LM741C and LM741A. Okay, so there is a difference in the temperature. So this is how the these are the packages and the body size. Okay, so let us see the pin diagram of LM741. The first, so totally it is having a 8-pin IC. So this is nothing but a dual-in package IC. So first pin is offset null, second pin is inverting input. So that this is what we have given it as V2, and a non-inverting input, that is third pin, and fourth pin is negative supply, and fifth pin is offset null, sixth pin is output, seventh pin is positive supply, and eighth pin is no connection. So this is a top view of LMC package. Okay, so you have to give the supply voltage, it is VDD and ground as plus or minus 15 volt. Okay, and the temperature, it is working from minus 55 to 125 degrees C. So here you can see the input offset voltage. Input offset voltage value is 1 millivolt, and input offset current is 20 nanoampere. Input bias current is 80 nanoampere. Input resistance is 2 mega ohm. It is higher in value, right? So I have given this is nothing but 2 mega ohm. Okay, and input bias current is 80 nanoampere, and the input is large signal voltage gain is 200 volt per millivolt, and the output swing is nothing but plus or minus 14 volt, and output short circuit current is 25 milliampere, and common mode rejection value is 95 deg. Okay, the common mode rejection ratio, it is not infinity, it is 95 dB for IC741. So this is what we are commonly using, so that is why I have chosen this one, and the slew rate is 0.5 volt per microseconds, and supply current is 1.7, and they have a supply voltage rejection ratio SVRR It is 96 dp, and the power consumption is 50 milliwatts. Okay. So this is nothing but the functional block diagram of the IC741. So you have second, third, first, fifth pin, seventh and fourth pin, sixth pin, and out. Okay. So this is a functional block diagram of IC741. So you can see the junction temperature is greater than the operational temperature. Okay. So now if you see the transfer curve for the VID versus VID versus V naught. Okay. So this is nothing but your slope. So this is nothing but your slope A. Okay. So and the slope is this is called as large signal voltage gain. So from this equation, it is evident that the op amp will amplify only the difference in the signal, right? Difference between two input voltage, and it will not amplify whenever the input voltage is same. And the output voltage V naught is directly proportional to that of the algebraic difference between the two input voltage, right? And the polarity of the this is depends on the difference between the input voltages. So if V2 is greater, you will get minus value. If V1 is greater, you will get positive value. Okay. So the use of this op amp is greatly enhanced by using the negative feedback. So it will avoid in reaching the output to the saturation. So if you see whenever if I use the for the ideal op amp, it is nothing but for increase in the VID, it will reach V saturation, and for negative direction, it will reach minus V saturation, right? But this will not happen for practical op amp. So it will be in so this region is called as a linear region. Okay. So this region is called as a linear region, and after this one it will reach a saturation. Okay. So if suppose V plus and V minus is my supply voltage, means the V saturation value is 2 less than the V plus value. Okay. So during the linear region, the curve is in the straight line, right? So whenever the value of A is large, means the curve get steeper, and it will nearly align itself with the vertical axis, right? So usually if I take the VID value is equal to 1 microwatts, and A value is equal to 10 into 10 power 5. So I will get V naught is equal to 0.2 volt. Okay. So if I increase the VID further after this point, okay, so it will rises, the V naught will increases further, and whenever it reaches this point, it get saturation. So this is called as positive saturation region, and this one is called as negative saturation region. And that value is nothing but plus Z and minus Z. Okay. So now let us consider a practical op-amp, practical inverting amplifier. So if you see the equivalent circuit of the practical amplifier. Okay. So this is how it will look like. This is my R1 and this is my Ri, and if I have a resistance that is Rf, and if I have R0, and here you're going to take the output, and this is my input voltage. Okay. So if I want to find the value of V0, so from this I can write, so the current flowing through this one is I. Okay, I can write V0 is equal to I into R0 plus A VID. Okay, so from this I can write this is nothing but your VID, right? So minus so VID minus is equal to IRF plus V0 I can write. So from this first equation I can write the value of VID is equal to V0 minus IR0 divided by A. Okay, so this is my first equation. So you substitute this first equation here. So you will get V0 plus IR0 divided by A is equal to IRF plus V0. So we can so if I bring this V0 that side, okay, AIRF plus AV0. So 1 plus AV0 is equal to, if I take I common, I will get R0 minus ARF. Okay, so this is my third equation. So from the first equation I can write so this is my I. So from the first equation I can write VA from this block I can write VA is equal to IR1 plus IRF, sorry, VA is equal to IR1 plus IRF plus V0. Okay. So this I can write it as I into R1 plus RF plus V0 divide by R0 minus ARF plus V0. Okay, so R1 plus RF plus AV0, R1 plus AV0 RF plus, if I bring this one I will get V0 R0 plus minus ARF V0 divide by R0 minus ARF. So if you see this two get cancelled out, so you will get R0 VI minus ARF VI, that is equal to R1 plus RF plus, if I take V naught common, I will get A R1 plus R naught plus RF. Okay. And A is greater than 1. So we will get minus A RF divided by R1. A R1. So you will get minus RF divided by R1. So next, from this equation, I need to find the value of input resistance, right? So in order to find the input resistance, I can calculate. So what is input resistance? That is nothing but VID minus I1. Okay, what is the current that is flowing through this? Okay, so I can write VID minus V1. Okay, so I can write this from this equation. I can write minus VID is equal to IRF plus IR naught plus AVID. Okay, so I can write so if I take VID common, I will get 1 plus A, that is equal to I into RF plus R naught. So I can write this RI is equal to RF plus R naught divided by 1 plus A. Yeah. So next I need to find the value of output resistance. So in order to find the value of output resistance, so I just paste this one and I am going to short this value, and I can take this one as ISC. Okay. So from this I can write, so I need to find the value of I naught. Okay. So this is, let me take this current as I naught. Okay. So what is I naught? I naught is equal to AVID divided by R naught. Okay. And we know that what is AVID, right? So from this equation, I can write minus VID is equal to I into IRF. IRF, right? So I can write VID is equal to I into RF minus I into RF. So you substitute here, you will get minus A IRF divided by R naught. Okay, because I have to open circuit this this RI. Okay. So what is my ISC current? ISC current is nothing but I naught plus I. Okay. So what is my I1? I current is nothing but I naught is nothing but A minus A I RF divided by R naught plus I. Okay. So what is I now? I is equal to VI divided by R1 plus RF, right? So you substitute here. So if I take I common, I'll get minus A RF plus 1 divided by R naught. So you can substitute here VI divided by R1 plus RF into minus A RF plus plus R naught divided by R naught. So we know that the R naught F, R naught F is nothing but VOC divided by ISC. Okay. So what is the output voltage? Output voltage is nothing but A into VI divided by ISC. So we substitute here. So A VI divided by VI R1 plus RF into R0 minus A RF divided by R0. So on solving, you will get R0 into R1 plus RF into A into A divided by R0 minus A RF. This A is nothing but AV. So if I substitute AV here, okay, so the AV the formula is V0 by VA is equal to R0 minus A RF divided by R0 plus RF into RF plus R1 into 1 plus A. So we substitute in this equation. If I substitute in this equation, I will get R0 into R1 plus RF into R0 minus RA RF into A divided by 1 divided by R0 plus RF plus R1 into 1 plus A into R0 minus A RF. So these two terms get cancelled out, right? So if these two terms get cancelled out, you will get R0 into R1 plus RF divided by R0 plus RF plus R1 into 1 plus A. So if I divide the whole term by divide and multiply with the whole term by R0 plus RF plus R1, I will get R0 into R1 plus RF divided by so this I can write it as divided by R0 plus R1 plus RF divided by R0 plus RF plus R1 plus R1 A divided by R0 plus R1 plus RF. So if I can cancel these two terms, I will get 1 plus R1 A divided by R0 plus R1 plus RF. And the numerator term I can write R0 in parallel with R1 plus RF. So I can write the overall term R0 F is equal to R0 parallel with R1 plus RF divided by 1 plus R1 A divided by R0 plus R1 plus RF. So here the R0 F value is always smaller than the R0. So this is the equation for the R0 F.